Now let's consider this setting. In this setting, our intuition suggests that this way of measuring the chances of head is the right thing. And indeed, in probability theory, this is known as the law of large numbers. If we toss coin enough times, then the measured score of the coin becomes arbitrarily close to the actual chance of seeing the head. So this way of measuring the bias or the score of a coin is perfect thing to do. And maybe that was the reason why we considered the population averages as an algorithm to begin with. But this is good when you have a lot of data. It is assuming that there's a lot of ratings in the case of restaurants that's available. Now in reality, we may have very limited data for some restaurants. Consider a newly opened restaurant. It might have only few ratings. Therefore, we may need to worry about what happens to such an estimator when we have very few observations. Back to coin setting, suppose we have only one observation. So let's say I toss this coin first time and first time I saw head. Now what? Well, my estimator would say the bias of this coin is 1 in favor of head. But that does not make sense because I've just got one observation. In sense, no matter what the bias be, my estimated bias would be 1 or 0 independent of the coin's actual chances. And this is clearly wrong. And it's clearly wrong in the sense that I've got so few observations, so I need to correct for them. Okay? Again, in the case of restaurants, each restaurant has different number of ratings. So simple average is definitely not the best estimator. It needs correction. Correction due to limited number of observations. Just the way estimating the bias of a coin needs a correction. What should we do? This is where another principle of probability comes to our rescue. It is known as the central limit theorem. It states that the error in the average estimator of the bias compared to the true bias behaves in a very specific manner. To be precise, let's consider the normalized error. That is estimated score minus the true score divided by the square root of the number of observations. This normalized estimator or error has a distribution called Gaussian or normal distribution with mean 0. This is named after a famous German mathematician named Carl Friedrich Gauss. Gauss lived from 1777 to 1885. He's also referred as Principes Mathematicarum. In Latin, it means that one of the greatest mathematicians in antiquity. Now here is how Gaussian distribution looked like. The variation in the estimation or the amount of error varies as true score multiplied by 1 minus true score. Therefore, if true score is 0 or 1, that is truly always tails or heads, that is always disliked or liked, then error is 0. Totally makes sense. Effectively, in that case, one coin toss is enough. On the other hand, if true score is close to half, then error is going to be large. The problem is we do not know a priori which is the situation. So we have to assume the worst possibility, that is error is the largest. In that case, the key takeaway from this mental experiment is that the error behaves like 0.5 divided by square root of number of observations or number of samples. Therefore, the true score is most likely 1 larger than the estimated score minus 0.5 divided by square root of number of samples and smaller than the estimated score plus 0.5 divided by square root of number of samples. This suggests a robust approach to order or rank or rate restaurants. 1. Assign scores to restaurants as average rating minus constant divided by square root of number of ratings that the restaurant has received. Now here, what is the constant C? In the case of the coin, it was 0.5. We shall discuss briefly how to choose C. 2. Use this score to rank order the restaurants as before. This way, if there is a restaurant which is new and has been rated very highly by very few people, think of the owner and his friends, it will not be able to fool the system. On the other hand, if the restaurant is truly remarkable, because its average is high based on a very large number of reviews, then of course the correction would be very small, and in which case average score would dominate. Now coming to the choice of constant C. Well, in the case of Yelp example, choice of C equals to 2.5 is great because the ratings are between 1 to 5. Alright, this is great. Now we have found a solution to combat the challenge of sparse data. And the solution is again very simple.